Series and parallel circuits. These things are not complicated. Okay, they're complicated when you first do them, but they're not super complicated problems. And they don't give you the solutions to everything, but they will help you understand what current is actually doing and how circuits behave and what voltage is and what current is. How to solve basic series and parallel circuit problems. Let's learn physics. If you want to see what they look like, I have a couple other videos of what they look like, and if you want to see how they work and what happens when you turn this off and what happens when you disconnect that and what happens when you add more resistors in series and what happens when you add more resistors in parallel, got a couple other videos there that'll be linked above and below or something. So a series circuit and a parallel circuit, ultimately the goal for both of these is to find the voltage and the current for each of those resistors in series and each of the resistors in parallel. And here's what we're going to do. A lot of times you're given a written description. You take that written description and you turn that into a sketch. You'll say that a 1, a 2, and a 3 ohm resistor are all connected in series to a 10 volt source. Draw it first. If you're not drawing it first, you're not picturing it probably as well as you could, and drawing provides a great way for you to label things on the diagram. Second, find the total resistance, or the equivalent resistance, or the resistance combination of those three. Then, after that, you find the total current. Find the current flowing out of the source. You want that, because you're going to use that. It's going to be used either as a check or applied to all of these things here. And then you're going to find individually the voltage and current for each of those, and then you check. At the end, you're going to have a check. Now what's constant in series that you have to keep in mind is the current. Current is constant in series. And you know perfectly well that whenever you plug into a socket, you can plug anything into any socket anywhere because the voltage is the same in parallel. And your house is wired in parallel. Voltage is constant there. There are quicker ways to solve these. Definitely quicker ways to solve these. But this gives you an introduction. It allows you to start thinking about the different circuits, analyzing them, and then later get the tricks to solve these a whole lot more quickly. Find the current for that individual resistor. Find the voltage for this one. Sometimes you can use simple ratios and fractions, but that's an advanced technique that we don't need to deal with until later. I have chosen, by the way, the same resistors, 1, 2, and 3, and 1, 2, and 3 exactly, so that you can compare side by side series and parallel circuits. We're going to start with the series circuit. Find the total resistance. You can just draw it. You draw the whole thing again. 10 volts, and there's another resistor. 1, 2, and 3. All you have to do in a series circuit is add them. 3 plus 2 is 5, plus 1 is 6. 6 ohms. 6 ohm resistor. That, by the way, as you learn to practice those little ohm symbols, that capital Omega in the Greek alphabet, that is a good time. So 6 ohms. This circuit and that circuit are electrically equivalent. The current flowing out of that, the current flowing out of that, exactly the same. The DC source of 10 volts, we're going to have a current flowing out of that direction or that direction. Remember, current flows in the positive direction if you're given like a battery or a cell symbol. But it doesn't matter. That's not the point of these problems. It's just to get the current and the voltage and look at the relationships. So, current flowing out of this. So we know that the resistance is equal to the voltage over the current. Please remember this is Ohm's law. Remember the equation, or write down the equation and use that equation on a regular basis. Remember that if you're solving for V, V is equal to I times R. Take that denominator, move it to the numerator over here. It's called what I call cross-moving. Link in the description for the mathematical technique that the math teachers don't like. But V is equal to I times R. Or, if you're looking for I, all you have to do, since this is a simple fraction on the left-hand side, just switch them. Do anything you can cross-multiply, you can cross-switch. So take that I and the R from the denominator on the right to the numerator on the left and switch them. So I is equal to V over R. Looking at this, you should be able to quickly algebraically manipulate that into a different version. So this thing right here, 10 volt source, 10 joules per coulomb. Voltage is energy difference per coulomb between 2 points. That's the energy source, and this is the only energy user, so 10 volts. 10 volts of energy used, supplied, 10 volts of energy per coulomb used. So 10 volts, 6 ohms. I is equal to V over R by switching those two. V divided by R, that would be 10 divided by 6, 1 2/3, 1.67 amperes. 3 digits are what I'm going to use. Always using 3 digits, because if you use 2, your answer is going to be a little bit different from your neighbor's answer, who's using 3. Enough different that you're going to think, oh, I probably got it wrong for the complicated ones, but you didn't. Maybe you did, but whatever. 1.67 amperes is what you get there. Use 3 digits. It helps in checking problems later. And then over here, okay, let's just do a side-by-side comparison. The overall resistance for the parallel, so 10 volts single resistor, is, we have to use the 3 to the negative 1 plus 2 to the negative 1 plus 1 to the negative 1, all to the negative 1. Use that in the calculator. Quickest way to do it. 0.545 amperes. Stop this video anytime you want to. It's a video. This is not me teaching you. In class, you should be sticking up your hand and asking questions when you have them. You can't do that here because this is a video, but you should be able to stop, go back. You don't need to see, you shouldn't actually see this all the way through. Not 0.545 amperes, but 0.545 ohms is the equivalent resistance of that. Now you look at these, oh look, as you add more in series, you get a larger resistance. And as you add more in parallel, you get a smaller resistance. In fact, this 0.545 always is going to be smaller than the smallest one. Smallest is 1 ohm, so 0.545 ohms is smaller than the 1 ohm. That 10 volts, same thing as over here. 10 volts supplied, 10 volts used. 10 volts divided by 0.545 ohms equals 18.3 amperes. That is a large current. Large current. As you add more resistors in parallel, you get a smaller resistance. Resistance, you know, it's resistance to flow. And with a smaller resistance to flow, you get more current. Here is the opposite trend. As you add more resistors in series, you get more resistance, and as a result, from the same source, you get less current. 1.67 amperes versus 18.3 amperes. Significant difference. This 1.67 amps, it's got nowhere else to go. These two are exactly the same electrically. So you take that 1.67 amps, 1.67 amps, and 1.67 amps, and 1.67 amps. You can take that current and apply it to all of those because you know that this and that are the same. Current flowing out of the source and through those is going to be exactly the same. Current is not lost. Current branches, it'll come across here, current will flow out, it'll hit that and split across those 3. But that 18 is going to split among those 3. But here, the 1.67 amps applies to those. As we talked about over here, the voltage is constant. That 18.3 amps, we're going to hold on to that to check later. But this 10 volts applies to that one, 10 volts applies to that one, 10 volts applies to that one. And so if you want to find the current, because I'm missing the current here, cross switch it, I is equal to V over R, V divided by R, this is 3.33 amperes. 10 divided by 1, this is 10 amperes. 10 divided by 2, that is 5 amperes. Don't fall into the error of thinking that the current is going to flow here and then preferentially flow across the closest one and then less across the farther ones. Nothing to do with it. These wires in these pictures don't have resistance. And so the current will naturally flow mostly through the lowest resistance. And as you get to the higher resistance, to the 2 and to the 3, the current goes down. And if you add those 3 up, the 10 plus the 5 plus the 3.33, you get 18.33, which matches this. It checks. Voltage is constant, and the currents add up to the source current, and it's 18.33 amperes. Also flowing through this one, that right there, that, because it splits, this 18.33 3.33 gets dropped into this one, and then continuing is 15 amps, or 15.03 amps, and the 15 amps flowing through there, and the 15 amps flowing here, combination of those two. And flowing back into the source, 18.33 amperes. Here it's the energy that splits. If you take a 1 Coulomb charge, because a volt is a joule per Coulomb, you take a 1 Coulomb charge and have it flow from this corner around in a circle. That 1 Coulomb charge starts here, goes through here, picks up 10 joules, because it's joules per Coulomb, increase of 10 joules of energy, and then it loses some energy and loses some energy and loses some energy, and then comes back to 0 at this point. So whatever energy this one supplies, it uses in that circle. So I know that the sum of the voltages is going to be 10 volts. Now I have to do the calculations. V is equal to I times R. I times R, 1.67 volts. And twice 1.67 is 3.34 volts. And 3 times that, it's 5. It's 5.01 volts is left over. 3 times 1 2/3. And then you add up the voltages. 5 plus 3 plus, okay, 5, 8, 9, 9.67, 10.01, 10.02. 10.02 volts is exactly the same as 10. We're using 3 digits, so it rounds off to 10.0 volts. There you go, that's what you have. The voltage adds up in series to be the source. Add those 3. But the current is constant. Different rules for the parallel. Voltage is constant, 10, 10, 10, and 10. And the current splits. So the largest current flows through there, smallest current flows through there, medium current flows through that one. That's basically how you do it. There are the checks. Once you do these a bunch of times, then you start playing with things and you look at the relationships, and you could just mechanically solve the problem if you wanted to. But if you're just mechanically solving that problem, you're not really understanding these. The next step after doing a bunch of these is to do series parallel combinations. That's a different topic. It's just basic introduction to solving series and parallel problems. Gonna have to do a video on series parallel combinations, huh? That's coming sometime. Thanks for watching Learn Physics. And thanks for that thumbs up too. Really helps a lot. New videos most academic weeks. Subscribe for more. I've even got education ideas, Freaky Physics Friday, and Tech Tip Tuesday. And for bicycles, motorcycles, and family adventures, it's my other channel, Bike Physics. You just learned physics.